Welcome back to my YouTube channel, and in this video I'm going to be talking about functions that are having arbitrary period. That is, in this particular scenario, this function are not going to be having a period of f of x is equals to f of x plus 2 pi. And this to say that 2 pi is the standard period for these other cases that we have been solving since the beginning of this series. So now we are going to be having a arbitrary period. Just say f of x is equals to f of x plus something like 4 or maybe even 6 or so, just an arbitrary period, not something that has to do with pi. So now this is how we deal with functions that are having arbitrary period. So first of all, we need to know how to get the constancies. What we are doing in Fourier series is getting the constant. So now to get the constant, we have a naught is equals to 2 over t, where t is the period, times the integral from 0 to t of f of x dx. That is for a naught, as simple as that. And therefore a n is equal to 2 over t, the integral from 0 to t of f of x cos n omega x dx. Now this omega here is equal to 2 pi over t, 2 pi over t. So whatever period that you are given, you are going to get this in order to get your value for omega, then you impute it into this. And now this omega has always been inside the formula, but no, we have never noticed because all the questions that we have been solving is has a period of 2 pi. So therefore, if t is equal to 2 pi, we would have it as 2 pi over 2 pi, which would cancel omega out, and therefore we just have cos nx. But omega has always been there since there. But in this particular scenario now, if we have our t as something like 4, let's say we have it as 4, this will become 2 pi over 4, which will become pi over 2 at the end of the day. So in this scenario, we would have to impute all these values there. So now let's move on with this. And so also our b of n is equals to 2 over pi, the integral from 0 to t, the period of f of x sine n omega x dx. So now let us solve the question here in order to clarify, in order to understand this better. So first of all, we know the first thing we have to get is our an, which is equals to 1 over, not 1 over this, we have 2 over, our period here is 0 to 2, which is 2 over 2, and the integral of 0 from 0 to 2 of f of x, which is equals to x times nothing times the x. So therefore 2 cancel 2, and this is going to be the integral of this. This is going to give us x squared over 2 from 0 to 2. This one is already 1 out. So if we put 2 into here, we are going to have it as x squared. We have 2 squared over 2 minus 0 squared over 2. And this is going to be equal to 4 over 2, which is equals to 2. So therefore our A naught is equal to the value 2, which is here. So now moving on, we have to get for our value of an. Our an is equals to 2 over our period t here, which is 2, and the integral from 0 to t of f of x, which is x, f of x is equal to x here, 0 to t, which is 0 to 2 of x cos n omega x. Now, what is our omega? Our omega is equal to 2 pi over t. And our t here is equal to 2. So therefore this is equal to 2 pi over 2. 2 cancels 2. This is equal to pi. So at the end of the day, this is equal to cos n pi x. At the end of the day, we will put our dx at the back of it. So 2 cancels 2 here. So we can continue with our integral by using integration by parts. So we have our u is equals to x, and our dv is equals to cos cos n pi x, we're going to be having sine n pi x over n pi, which is the constant here. So this is what we are going to be getting. So now we just use it here where our an is equal to the integral uv x sine n pi x over n pi from 0 to 2, then we have minus the integral from 0 to 2 of v du, which is 1 over n pi. We are bringing our over n pi here outside. Then we have our sine n pi x dx. So now this our value. If we put 2 here, we are still going to have like this pi here is going to make it 0. And if you put 0, this is also going to be 0. So at the end of the day, this entire thing here is going to give us 0, which will leave us with this. This over here, we will have minus 1 over n pi. And if you integrate this, it's going to give us cos, no, it's going to give us minus cos n pi over n pi. And we have it from 0 to 2. So we just continue this and we have it as minus 1 over n pi, and the n pi we can also bring it outside, so that is n square pi square of cos, the minus here can multiply outside, so that is here we have our minus cos n pi from 0 to 2. The minus can multiply this, so they cancel out. And therefore, if we just repeat our values, we have 1 over n square pi square. We have this as cos n pi x here. Let's not forget our x, n pi cos n pi x. So now this is going to become into brackets. When x is equal to 2, we have cos 2n pi, and when x is equal to 0, we have minus cos 0, because no matter what is done at 0. So then we just analyze this. This is going to become 1 over n square pi square of, now this is going to become minus 1 raised to power 2n. Then we have minus 1 also. So in this particular scenario here, our minus 1 is going to be, our minus 1 here raised to power 2n is going to give us plus 1. Our minus 1 is going to give us plus 1. That is to say, because of the square here, that is the 2 is going to be the main value of the power. So we have minus 1, give us plus 1, and we it will be 1 over n square pi square of into bracket 1 minus 1, which will end up giving us 0. Therefore, our value for an is equal to 0. We can put it up here. Our a naught is equal to 2, and also our an is equal to 0. So now that is for our an. So we move to our value of bn, which is 1 over no, 2 over t. Our t here is 2. The integral from 0 to 2 of f of x, which is our x sine n pi x, due to the fact that I've already gotten our omega as pi. So n pi x, then when we continue, we 2 cancels 2, we just use integration by parts. U is equal to x, and dv is equal to sine n pi x. Du is equal to dx, and we have our v is equal to minus cos n pi x over n pi here. So now since I have gotten this, we can just use our integration by parts, we have Vn is equal to, this integration here is going to be equal to uv, we have minus x cos n pi x over n pi from 0 to 2 minus the integration from 0 to 2 of v du, which is minus cos n pi x dx over n pi. We just put the n pi 1 over n pi here, and the minus here will also cancel this minus here, so this will just become plus at the end of the day. So now moving on with this here is going to give us now if you put the value of 2 here, we are going to be having this as minus 2 over n pi of into bracket. Now when minus 2 over n pi of cos 2n pi, which is inside here, and we also have 0, which is, if 0 is here, it multiplies everything and that cancels out at 0. So then for the other side here, we have plus let's think about this, plus 1 over n pi, and then the integration of this is equal to sine n pi x over n pi from 0 to 2. From 0 to 2. So now let's analyze this. Let's analyze this. This is going to give us n pi x 2n here. So let's analyze this. This is going to give us minus 2 over n pi, and this is minus 1 raised to power 2n plus this n pi comes out, 1 over n squared pi squared sine n pi x from 0 to 2, which everything here is going to give us 0. So now let's move here. We are going to be having this here. Since minus 2 here, this is going to become positive because of the even sign here. We have bn is equals to minus 2 over n pi. So that is it for this. So this is positive, and this here is going to give us 0. So therefore, our final answer, we have our an, our a naught is equals to 2, and our an is equals to 0. So therefore, this is going to what we are going to use. And our final answer, f of x will be equals to an over 2, which is a naught over 2, that is 2 over 2, and we also have but since the sign here is minus, we have minus 2 over pi, which is the ones that are apart from n. Then we have our summation so that the n can enter inside. We have the infinity n from n equals to 1 to infinity of sine n pi x, yeah, of sine n pi x, because don't forget that sine omega x, so sine n pi x, yeah, that is going to be, this is the Fourier series for the question in which we are given earlier. Thank you very much.